Good afternoon. My name is Vivek Kumar. I'm a faculty here at the Jackson Laboratory. I want to thank the organizers for allowing us to present this work and for putting together this wonderful conference. Today I'm going to tell you about work that we've been doing in my lab on a machine vision-based frailty index for mice. This is work we've been doing for about a year in collaboration with Gary Churchill here at the Jackson Laboratory and the Shock Center at the Jackson Laboratory. So needless to say, for this crowd, frailty is one of the, probably the best measure of biological aging. Clearly, quantifying frailty is important. Frail individuals are at increased risk for diseases, death, negative outcomes from hospitalization. So the process of quantifying frailty becomes clinically very relevant. Mice serve as a really great model system for mechanistic studies, for interventional studies, especially large-scale interventional studies. So the frailty index has been translated to mice, where a trained expert assesses every animal on a set of age-related health deficit indexes. So for instance, we can look at vision loss or tail stiffening. And this trained expert scores that mouse on a scale of 0, 0.5, or 1, and then these numbers are aggregated to produce a frailty index of the animal. Now, anytime you have a human in the loop where there's training involved and there's subjectivity, there's an increased amount of noise in the system from the trained human, i.e. Humans actually can increase variability in frailty indexing. And certainly in terms of scalability, humans can be an impediment if you want to study thousands of animals. An automated system can be much more not just reliable and replicable, but scalable. So what we're interested in essentially doing is building an automated frailty index that uses computer vision. And our hypothesis is that biological aging produces changes in behavior and physiology that are encoded in video data. And the goal here is to develop an efficient and scalable automated visual scoring frailty index using computer vision. My lab has been working in this space of applied computer vision for several years at the Jackson Laboratory. We've developed systems to look at track animals under difficult circumstances. We've developed methods for action detection. So here's a neural network that predicts when the animal is carrying out grooming or is not grooming. So you'll see this changes from red to green when the animal is grooming. This actually works quite well at human overperformance. We've developed methods of analyzing key points of the animal to understand the pose of the animal, and this allows us to look at gait, to look at behavior at very high resolution. So this is the kind of work we've been doing, and here's a set of papers that from our lab over recent years. So we don't have to be aging experts to know that this is a young mouse and this is an old mouse. And this right away told us that information about aging and health is encoded in video data. And the question was, can we extract enough of these to really construct a useful frailty index? So the process is described here. We take 568 mice. These mice go into a 1-hour open field assay, just like the video I showed you earlier. From this, we extract information through pose estimation, segmentation, tracking, and these are information like traditional open field measures, but also high resolution information like gait information, like grooming information, and then some engineered features. After the testing, these mice also, they go back to the shock center and their manual frailty indexing is carried out. This provides us ground truth labels in all these animals. And we train models based on these features to predict the manual frailty score, and this is what we call the automated visual frailty index. So let me go into this with a little bit more detail. So our data set is shown here. we have animals from a few weeks old to about 130 weeks old, roughly equally distributed between males and females. And right away, you can tell that, score differences start to emerge. So for instance, the red score here tends to have higher frailty score, manual frailty score compared to the other scores at the same age. So what type of features can we extract? So I mentioned a few, such as open field, gait. We also can start to look at things like morphometric features. So here, for instance, we are interested in the width of the animal. So we can look at the minor axis of the ellipse fit, and we can use actually really careful measurements between the rear feet, rear paws of the animals as also a measure of the width of the animal. And both these correlate with the frailty index in a positive way. And we also look at very gait measurements. These are classic Hildebrand type measurements like stride length, step length. We can also look at posture-based measurements of the animals because our animals are from the top down. So we can look at how much swagger an animal has. So like how much does the tail move over the midline in that stride cycle. And these also correlate with the frailty score. We also engineered features. So here we're interested in flexibility. So we essentially constructed a flexibility index where we take these 3 points across the animal and we extract distances and angles between them to determine how flexible the animal is in this XY axis. And what we find is, this assay itself works well. However, we found a kind of a reverse trend. So we expected the flexibility to decrease as the animal gets older. But in fact, we find as the animal becomes more frail, we see higher flexibility. And the reason for this we think is because the XY direction is not very good to look at flexibility. The Z direction may be a better metric of what flexibility is. Older animals tend to kind of go and they won't move as much and they kind of curl up and they just sit in a corner. So we started to look at this flexibility in the Z direction. We quantified this using a rearing metric. So every time the animal crosses this yellow line, we call it a rear event. And in fact, we do find that rearing correlates highly with frailty status, with the more frail animals rearing much less than the less frail animals. So these are kind of the individual features we generated. In the end, we ended up with 38 features, and then we extract distribution metrics from those features, which go into a classifier. And we trained 4 different models. So we trained a penalized regression, a support vector machine, a random forest, and a boosting algorithm. And we have 3 different metrics to measure performance. On the first 2 metrics, MAE and RMSE, we want lower metrics, that's better performance. On R squared, we want higher, that's better performance. And in the end, we ended up, and we're predicting here 2 things. We're predicting these set of models here are predicting age, and on the right, the models are predicting the frailty score. And I'll focus on the frailty score, and you can see the random forest tends to perform fairly well for both for frailty as well as for age. So random forest is here. So we picked random forest as our model to carry on in the project. We're also, in terms of performance, what we find is that the random forest allows us to predict frailty within 3.9% plus minus 0.3%, which, if you remember how the frailty index is scored, is akin to a difference in scoring of 1 frailty item differently by 1 point, or 2 frailty items differently by 0.5 points. So it's actually quite good. In terms of prediction of age, we can predict age to about 13 weeks plus minus 1 week. So we're getting good prediction of both frailty and age in our video-based modeling. So we're also quite interested, we want models that are interpretable. We don't want these black box models. So we spent a lot of time trying to understand and interpret the models, the random forest model. So here, we're just showing all the features and the importance of each feature. And we've broken down the animal population into 3 quartiles. The young animals, the middle-aged animals, and the older animals. And what we find is that there are lots of features that are being used by the model to predict frailty. It's not simply relying on 1 or 2 features. It's really using a large number of features to make predictions. And furthermore, depending on the age of the animal, it uses different sets of features. So this was good to see because we want the model to use as diverse information as possible to make a frailty score. So we felt really, like this approach is working. In addition to looking at kind of the feature importance of individual features, we also started to look at interaction between features, the interaction strength between features. And these also turned out to be important. So for instance, almost all the features we looked at had some level of interaction that was important in our model. And some of them were quite important. So for instance, step length and step width interact. And so when you have high step length and high step length and high step width, the model predicts a positive frailty score. However, at certain point, when you have a step length of 0.25, a step width of 0.3, the model actually starts to predict a lower frailty score. So this interaction is not linear, and this interaction is important to capture. So this was another finding that we had in the modeling. So in the end, we've been able to construct a fairly robust frailty index just using a 1-hour open field assay. We're very interested. We feel this is a first step. We're really interested in extending this. All the work was done with C57 Black 6J mice. We need to extend this to genetically diverse mice. We're quite interested in not just predicting frailty, but mortality and along with frailty. We think adding automated tasks that assess cognitive function or motor function in an automated way can actually add a lot more information and create much more robust frailty index. We also think, 1-hour recording is let's face it, a really short time. We'd like to do this in a home cage environment where we measure long periods of time with multiple animals, so we can start looking at social interaction. We can look at when the animal's eating, drinking, all these things. So we really feel that long-term monitoring can add a lot of value here. And then finally, we would like to start to apply this to interventional studies in aging, because ultimately we feel these automated methods are really well suited for intervention for interventional studies. So that's about it. Let me just acknowledge the people who did the work here. So Lanani and Gautam I mentioned already, intern and biostatistician. The work couldn't have been done without the Shock Center and Gary Churchill. And so we really want to thank Gary Churchill and his whole team here. And then finally funding from the Jackson Laboratory. So thank you very much.